Hello everybody. Today we'll be talking about a rotational view of the atmosphere, Chapter 4 in the text. In particular, the focus of today's lecture will be on vorticity, an introduction to rotational motion in the atmosphere. So recall that there are two main goals that we're focusing on in dynamic meteorology. The first is understanding the structure of atmospheric motions, that is, diagnosis, and the second is prediction of future atmospheric motions, or prognosis. So far, concepts that have involved balance, including geostrophic balance and hydrostatic balance, have largely focused on the diagnosis component. Whereas we will now focus on prognosis. We're now interested in using our understanding of rotational motion in the atmosphere in order to try to derive equations which govern the future behavior of atmospheric motions. And so the focus of this will be on rotational motion, since that is the dominant form of motion in the atmosphere. In particular, we'll be focused on what is known as vortex dynamics, where a vortex in this case is defined as an area of closed circular or near circular fluid motion, where there is a tendency for a rotation or for rotation in the underlying flow. By definition, vorticity then is a measure of the local spinning motion of the flow. So it consists of a vector. So remember that vorticity here is a vector field and not a scalar quantity. And it denotes the local axis of rotation and the local magnitude of rotation, or the rotation rate about that axis. So in accordance with the Helmholtz theorem, we know that any 2D flow, that is, flow along the surface of the Earth, can be thought of as being composed of both a rotational and a divergent component of the flow. The rotational component then will have zero divergence associated with it, and the divergent component will have zero rotational component associated with it. Note that rotation in this context is important for the development of high and low pressure systems, and in particular we're going to be interested in determining the interplay between rotation and divergence and vertical motion. Consider an arbitrary flow field, here denoted by the black lines, and an arbitrary Eulerian region which is embedded within this flow, denoted here by the light blue region. Recall that an Eulerian region is a region within space which is not moving with the flow, that is, has a fixed spatial location. The flow field can then be described in association with this region as a combination of motion of fluid in and out of this region, as well as a rotational component, which we'll investigate earlier. First of all, in order to focus on the divergent component, that is motion of fluid in and out, we see that this is closely associated with what is known as Gauss's theorem. So for a particular region of the flow then, if we integrate over the velocity field dotted with the normal component, this is then equivalent to the integral of the divergence of the flow over the corresponding region. So the idea of flux, that is flow into or out of a region, is associated with a region that is a finite sized volume, whereas divergence is a quantity that can be calculated pointwise at each location within the flow. The divergent component of the flow is then associated with a single point in space, and can be computed for each given flow field. The 3D divergence operator is something that we've seen previously in these lectures, and it is the sum of the partial derivatives of each of the velocity components with respect to their corresponding coordinate direction. So here it's equal to the partial derivative of u with respect to x plus partial derivative of v with respect to y plus partial derivative of w with respect to z. And this gives the full complete 3D divergence. However, we will also be interested in the 2D divergence operator, that is the one which exists along a horizontal plane, whether it be a height surface or a pressure surface. And in this context, it's simply the first two components, that is the partial derivative of u with respect to x plus the partial derivative of v with respect to y. Rotational motion, as I mentioned earlier, is the second component of the flow associated with this region. So this is associated with vectors which are tangential to the flow field at each point. The idea here then being that the flow field at any point can be decomposed into both a normal component to the region and a tangential component to the region. Hence, it's logical to assume that any flow field can be decomposed in this manner. Rotational motion then is associated with circulation of the flow. So a particular region has a corresponding circulation associated with it, which is equal to the contour integral around the outside of the region of the velocity field dotted with a tangential vector along the region's boundary. So circulation is effectively then a measure of the rotational part of a flow associated with a particular region. It is an analog to angular momentum of the flow, and so induces a conservation law then associated with angular momentum, which we will see later in this chapter. The direction of the circulation is then defined by the direction in which the flow goes around the circuit. So for cyclonic motion, we then say that it goes around in a counterclockwise direction in the northern hemisphere, and for anticyclotic motion, we say that it goes around in a clockwise direction in the northern hemisphere. It'll become clear later as why these definitions arise. In the southern hemisphere, the opposite definitions are true. That is, cyclonic motion is associated with clockwise rotation, whereas anticyclonic motion is associated with counterclockwise motion. Analogous to Gauss's theorem, which we applied earlier for the divergence of the flow over a region, there exists a corresponding theorem describing the connection between circulation and vorticity. So circulation is a concept which is valid along a closed curve surrounding a region, whereas vorticity is the concept which is associated with flow at a particular point in space. These concepts are then connected via Stokes' theorem, where we say that the circulation about a curve is going to be equal to the total integral of the vorticity vector field curl of u dotted with a surface normal which points perpendicular to the surface being integrated. If this surface, for instance, follows the surface of the sphere, then the dot product is with the normal vector to the surface, or the vertical basis vector. So the vortical component of the flow is then used to describe rotation about a single point. So consequently, you can say at a single point how much of the fluid is circulating about this point. Here is a plot in which we can see a 500 millibar height field in combination with corresponding wind vectors. Here if you follow closely along the wind vectors shown in this particular plot, you'll notice the existence of a highly vortical region closely associated with the low pressure denoted at a geopotential height of 5,474. So here you can see clearly the evidence of vortical motion around that particular low pressure. With the geostrophic balance, positive vorticity is actually associated with cyclonic rotation in the northern hemisphere, that is, rotation about a low pressure system. Consequently, you see the connection between vorticity and pressure in the atmosphere. Predictions of changes in vorticity then are closely associated with predictions in the changes of pressure in the atmosphere, or analogously, predictions of changes in geopotential height. In fact, the first computer forecasts only predicted changes in vorticity, and using changes in vorticity, it diagnosed changes in pressure. Even with this simplified forecasting system, these computer models were still able to do a decent job of actually modeling the atmosphere. Analogously, negative vorticity is associated with anticyclonic rotation. That is the type of rotation you would normally see about a high pressure system in the northern hemisphere. So recall that the 3D vorticity is associated with the curl of the vector field, and that it is a vector. Since it's a curl, it is a vector quantity. The vector quantity then denotes the local axis of rotation of the flow. The two horizontal components are associated with overturning motions and vertical wind shear because they are dominated by these vertical derivatives of the horizontal wind velocity. Whereas the vertical component represents vorticity confined to a horizontal surface. This is the type of motion that we're going to be primarily interested in because this is the type of vorticity associated with cyclonic systems, for instance, and the dynamic evolution of large-scale weather systems in the mid-latitudes. So the focus will then be on this third or vertical term of the 3D vorticity vector. So for diagnostic purposes, the vertical component is going to be the most important, and hence we define a 2D vorticity associated with this quantity, which we'll denote with the Greek character zeta, and that's simply given by the partial derivative of v with respect to x minus the partial derivative of u with respect to y. This is also known as the relative vorticity, since it is computed locally and does not take into account rotation of the coordinate system. If we look at this on the globe then, for low and high pressure systems, we then anticipate that the relative vorticity about those points will be either counterclockwise in the case of a low or clockwise in the case of a high. Again, we're assuming that everything is in the northern hemisphere in this case. In addition to this, we also have a component of angular momentum, which is associated with rotation of the Earth, that needs to be taken into account. Using the 3D vorticity vector again and focusing purely on the vertical component of this vorticity vector, this quantity is then going to be referred to as the relative vorticity of the flow. So recall that conservation of angular momentum must occur in an inertial frame, that is, one which is constant with respect to both space and time. However, in the derivation of the equations of motion, remember, we are using a rotating frame, that is one which varies along the surface of the sphere and one which varies in time in accordance with rotation of the Earth. So computing relative vorticity is only one contributor to the overall vorticity of the flow. We have to also account for rotation of the planet, which appropriately enough we will be referring to as planetary vorticity. Now, planetary vorticity is associated with rotation around the axis of the Earth. So you'll observe, first of all, then, that the vertical component of the vorticity vector will be affected differently depending on where on the Earth's surface we are. In particular, at the North Pole, the vertical velocity vector will be exactly aligned with the axis of rotation, and so we anticipate that planetary vorticity will be maximal at the North Pole. As we go to the equator, the vertical velocity vector is actually perpendicular to the axis of rotation, and consequently there is zero contribution to the vertical component of the vorticity vector from planetary vorticity in this case. In between the two, we see basically partial rotation, that is, some contribution from rotation of the Earth to the vertical vorticity vector. The definition of planetary vorticity that then arises from this observation is that the component of the vorticity due to rotation of the Earth is going to be called planetary vorticity, and it is denoted by subscript F, which you'll notice is the exact same as the Coriolis parameter that we introduced early in these lectures, and that's equal to k dot the cross product of the velocity field associated with rotation of the Earth, or exactly 2 times omega times sine of latitude. Planetary vorticity then is the contribution of angular momentum due to the rotation of the planetary surface. So computing this, given the rotation rate of the Earth, then gives a planetary vorticity of approximately 1.4 times 10 to the minus 4 inverse seconds at the North Pole, 1 times 10 to the minus 4 inverse seconds at about 45 degrees north, and 0 at the equator. The absolute vorticity, or total vorticity, which we'll denote by Greek character eta, is then the sum of the relative vorticity and the planetary vorticity. And this is in fact the quantity that we need to worry about when taking into account conservation of angular momentum. So absolute vorticity then, being the sum of relative and planetary vorticity, will be defined as dv dx minus du dy, which is the relative vorticity, plus f, which is the Coriolis parameter or the planetary vorticity. So notice that vorticity in this context then is a magnitude. That is, it is denoting a rotation rate about the vertical axis. So this concept arises immediately from the idea that the absolute velocity is equal to the sum of the Earth's rotation velocity and the local velocity. in combination with the linearity of the curl operator, which is a derivative and hence inherits linearity properties. So one might wonder why we never take into account rotation of the Earth when computing the divergence. That is, there is no concept of absolute divergence, but there only exists a relative divergence, which is computed from the local velocity field. Well, if one was to actually compute the divergence of the rotational field associated with rotation of the Earth, one will quickly observe via this calculation that the rotation of the Earth is a non-divergent flow. That is, it is purely rotational, hence has zero divergence, hence the absolute divergence of the flow is actually equal to the relative divergence of the flow. So comparing rotational versus divergent flow, rotational motion, denoted by zeta, is defined by di x minus di u di y. It has a typical scale of about 10 to the minus 5 1/seconds, for large-scale mid-latitudinal systems. This can be observed immediately by noting that the vortical component has a scale of velocity divided by length. For divergent flow, although the velocity scale is also although the corresponding scale is also velocity divided by length, the two terms in the 2D divergence operator actually approximately cancel each other for atmospheric motions, and consequently divergent flow tends to be about 10 times smaller than corresponding rotational flow. Hence, rotation in the atmosphere is approximately an order of magnitude more important than divergence. So this explains to some degree why vorticity is going to be the focus of our predictive equations, because it is simply much more important than divergence. So at the simplest level, the atmosphere can be described then using vortex dynamics. That is, vorticity should be the focus of our prognosis of the atmosphere. These vortices are dominated by rotation and curvature. However, using the definitions of vorticity that we derived, we can ask the question, do all curved flows actually have vorticity? And further, are all flows with vorticity curved? The answer in general is no. Not all curved flows have vorticity, and not all flows with vorticity are curved. In fact, there exists a class of vortical flows which are sheared. For sheared flows, they will induce rotation if you were to place an object into the flow, but they are not curved themselves. To see a simple example of this, consider, for instance, a atmospheric flow which has a horizontal shear associated with it. We place a stick which points north-south into the flow and observe the consequences of the flow field then interacting with the stick. In particular, you'll notice in this case that the horizontal velocity u does vary in the north-south direction, whereas the meridional velocity v is zero throughout. Consequently, there is a non-zero zeta associated with this flow. So what happens to the stick under this flow field? One will quickly observe, in fact, that the stick will rotate due to a faster flow in farther north and a slower flow to the south. So here we have pointwise rotation, but no curvature associated with the flow. So this is what is known as a sheared flow and has non-zero vorticity associated with it. So there are two types of flows then which have vorticity, both rotational flows, that is vortices, as well as sheared flows, such as the example given here. So there are a number of concepts which then arose throughout our discussion of vorticity that are summarized here. Recall, relative velocity has components u, v, and w in the zonal, meridional, and vertical directions. The 3D vorticity vector is obtained by taking the curl of the relative velocity field. And the relative vorticity is a scalar quantity then, which is obtained by dotting the vertical basis vector with this curl. And it is simply the vertical component then of the 3D vorticity vector, defined by di v di x minus di u di y. The absolute vorticity is again a scalar quantity which takes into account the absolute velocity field and hence accounts for planetary vorticity, or rotation of the planet, and that is defined as zeta plus f. Planetary vorticity here is equivalent to the Coriolis parameter, which we used in Chapter 1, and it is given by k dot, the curl of the velocity field associated with the Earth's motion, or simply 2 omega times the sine of latitude. So that's all for today. Next time we'll talk about deriving a prognostic equation for the vorticity field.